Section 8.3 is on graphing something called a reciprocal function. Another way of referring to it would be a rational function. And so there's three things we want to do. We want to talk about a part of the graph that's called an asymptote. It's kind of this weird looking part of the graph that the lines go off to either positive or negative infinity. Then we'll talk about how to find the domain and range, and then finally we'll actually graph a few as well. Okay, so this picture right here shows you the parent function for all reciprocal functions, and they're called reciprocal functions because this is a reciprocal of y equals x. If reciprocal means you flip it over, so 1 over x. Okay, the actual name for this is called a hyperbola, similar to a parabola in certain respects. The domain and the range is basically any non-zero number. The reason that x cannot be 0 is because if you were to plug 0 in right here, you would get 1 over 0, and you can't divide by 0. If you try to do it on a calculator, it will give you an error. Okay, this doesn't have any intercepts. You can see it never touches either the x or the y-axis. And I just want to show you why you're not allowed to divide by 0. It's kind of interesting to understand this. You talk about this more when you take a calculus class, but at least for now we can get a little bit of an understanding. Okay, so let's start by plugging in numbers that are really close to 0, that get closer and closer. So we'll plug in 0.1, we'll plug in 0.01, plug in 0.001, plug in 0.0001, okay, and so on. You'll be able to see the pattern. These numbers right here, they're getting closer and closer to 0. That's what that notation means. X with an arrow going to 0 means x is getting closer to 0. 1 divided by 0.1 is 10. This one is 100. This one's 1,000. This one's 10,000. So you can see these numbers here. As x is getting smaller and smaller, the y value is getting bigger and bigger, and that's what this part of the graph means. X is getting closer and closer to 0, and this line is shooting up eventually towards infinity. Theoretically, if you were able to divide by 0, it's almost like you're getting infinity as an answer. And like I said, you'll study that more when you take calculus. You talk about something called limits, but for now, that's the main idea. You can't divide by 0. Okay, just to drive that point home, there's a crazy looking cartoon here that hopefully will impress upon people the dangers of dividing by 0. Okay, the domain of a reciprocal function is basically x can be anything except what causes the denominator to be 0. So if you look at this one right here, if we were to set this equal to 0 and solve for x, we would get x equals -2. Okay, x equals -2. That means you would say the domain for that function is basically x does not equal -2. X equals everything except for -2. Same thing right here, x cannot be 5, so the domain would be x does not equal +5. Okay, right here again, x could not be 0. So basically these numbers here tell you where it's not defined, and in order to state the domain you would just say x cannot be that number, cannot be 0. Alright, let's do just one more of these. It says determine the value of x for which this is not defined. Well, that's not going to be defined when that is equal to 0. So we'll set it equal to 0 and subtract 5 from both sides. And then when we divide both sides by +2, we would get x equals -5 over 2. So how do we say that as a domain? We would say the domain is x can be anything except for -5 over 2. That's how you would state the domain for that function. Okay, asymptotes. The asymptotes, there's two kinds of asymptotes. There's what's called a vertical asymptote and a horizontal asymptote, and I'll show you on this one first the vertical. The vertical is this red line right here. Okay, an asymptote is basically a line that this function gets really close to, but it never touches. You can see this blue line is going higher and higher. If you were to follow that up to infinity, it would get super close, and same thing down here. This would get really close, but it would never actually touch that line. Okay, that is called a vertical asymptote, which I'm abbreviating VA, and the equation for that is x equals 3. How do I know that it's x equals 3? Because x equals 3 is what makes the denominator be 0. Okay, same thing right here. So if you can't tell by looking at the picture, you can just look at this. The vertical asymptote for that one is whatever's going to make that 0. And x equals -2 makes that 0. And you can see from this picture, that vertical line that I just drew in red, that is the line x equals -2. Okay, if we found the vertical asymptote, we also found the domain. Since x equals 3 is the asymptote, that means the domain is x cannot equal 3. Okay, why can't x equals 3? Because there's an asymptote right there. You you'd be plugging in 0 to the bottom. Same thing right here. The asymptote is x equals -2. That means the domain is x does not equal -2, because if it does, you'd be dividing by 0. Okay, how about the range? The range is referring to another type of asymptote. That's the horizontal asymptote. And you can see it right here, this purple line. You can see this gets really close to it here, this gets really close to it right here, but it never actually touches it. So the range is basically y does not equal 0. And that's because the horizontal asymptote is y does equal 0. Okay, right here, if it were just this graph, it would be the same, but notice that -1 actually shifts the graph down 1. So you can see this new asymptote right here is not y equals 0, it's y equals -1. So that's the horizontal asymptote, y -1, because that -1 moves the graph down 1. It's kind of like what we did in prior chapters with parabolas or other types of functions. Okay, so that means the range for this is y can be everything except for -1. Y does not equal -1. Let's see if we can do one more here. Let's do number 2b right here, or I should say letter 2b. Okay, so let's do this. So first of all, the vertical asymptote is x equals -1. That means the domain is x does not equal -1. Okay, the horizontal asymptote and the range, well, the horizontal asymptote is this number. We basically moved this graph up 5 units. And I'll just draw the vertical one too. The vertical one is right there. So you can see those lines get very close to the red dotted lines. They never touch though. So the horizontal asymptote is y equals 5, and that comes from right here because we moved the graph up 5. That means the range is y does not equal 5 because it never actually touches that number. So hopefully that idea makes sense. Okay, one other thing we want to talk about before we talk about graphing it, that all the transformations that we talked about in prior chapters still apply right here. So simple example, suppose we had f of x equals 3 over x minus 2 plus 4, and we're comparing that to this parent function. Remember actually let me call that g of x. F of x is this right here. Okay, so what does the red function do? This is g of x right here. What does g of x do to this function? And it does 3 things. This number right here is going to vertically stretch it by 3. And it stretches it because basically any number bigger than 1 is going to stretch it. By the way, if that were negative, okay, that's what this says down here. If that were a -3, the negative would flip it over the x-axis. Okay, it's positive in this case, so that doesn't happen. This right here, remember the saying add to x, go left, and add to y, go high. Okay, add to x, go left, add to y, go high. This one, because we're subtracting from x, we're not going to go left, we're going to go right 2. And add to y, we're adding 4, so that means we're going to go up 4. So all the transformations that we've studied previously still apply to these examples. Okay, so let's graph this function, and it's actually a better idea to make a table of values than it would be to try to stretch and shrink this stuff, because we don't know easily what a vertical stretch of 2 looks like. So basically we'll graph it using a table of values, and then afterwards we'll compare and just see that our picture agrees with what we would expect. So this one is going to move it right 4, it's going to vertically stretch it 2, and it's going to go up 2. So let's verify that that's the case by the time we finish. Okay, the first ways that we should start this graph is by finding the 2 asymptotes, because that's how we base all our graphs are. So the asymptote is going to occur at x equals 4. That's the vertical asymptote. So I'm going to draw that. Here's the line x equals 4, so we know if we draw this graph correctly, it should never touch that right there. And the horizontal asymptote is going to be right there. Horizontal asymptote is y equals 2 because we've shifted that up 2. So here's our point. And notice this, we basically 2 regions here. We get region A to the right of that, and to the left of that, region B to the left. So our graph should actually have 2 parts to it. It should have something in region A, something in region B. Okay, how can we find it? Well, our key value here is x equals 4. So let's get a couple points to the right and to the left of that. And actually, just to give you an idea of which points that we should pick, the best points to pick here would be, you want to see if you can find any intercepts, any either x-intercepts or y-intercepts. Those tend to be the best type of ones to look for. So let's take a look at that. Let's do this. Let's find x-intercepts and y-intercepts. and then we'll add them to the graph. So the x-intercepts occur whenever y equals 0. So I'm just going to take this function and set it equal to 0 and see if we can solve that, which I think we'll be able to pretty easy. So we'll move that 2 over to the other side, so we get negative 2 equals 2 over this. Okay, then actually that's a fraction, so we can basically cross multiply those. So 1 times 2 is 2. Negative 2 distributed to this would be negative 2x, and then negative 2 times negative 4 would be positive 8. So we'll subtract 8 from both sides, and we'll get negative 6 is negative 2x. So divide by negative 2, so we get x equals 3 when y equals 0, because we found that point when we plugged in y equals 0. So we have a point 3 comma 0 on that graph. So let's put that in here. Here's 3 comma 0 right here. And then really all we need to know is this going to go up or down? So it could either go down this way or it could go up this way. We don't know yet, and here's how we can find out. We basically just need to find any point that's in between x equals 3 and x equals 4, and that will be able to work for us. So I'll just show you how to do this. Let's do 3.5, and then just to show you, let's do a point a little bit to the left of that. We'll do 0, because remember we said we're finding the x and the y-intercepts. So the y-intercepts occur just like the x-intercepts occur when x equals 0. The y-intercepts occur when, y-intercepts occur when x equals 0, x occurs when y equals 0. Hopefully I didn't say that backwards. So let's do this. So that means y equals, we're going to plug in 0 for x. And remember, you can plug in 0 for x on the bottom. It's just that the bottom can't be 0. But if I plug in 0 for x, it's not going to be 0. It's going to be negative 4. 0 minus 4 is negative 4. We still have that plus 2 here. So this right here is negative 2. Negative 2 plus 2 equals 0. So that means the point 0, 0 is, let's just double check that we did that correctly. Nope, didn't do that correctly, sorry. 2 over negative 4 is not negative 2, that's negative 1/2. You've got to be obviously more careful than I am when you fill these out. So we get negative 1/2 plus 2, and that actually equals 1.5 or 1.5. Okay, so this is, yeah, that point seemed a little bit strange when we first put it in. So 0, 1.5, this will be able to give us a nice picture here to tell us where we're going. So 0, 1.5 is right here. Now you can see that's gonna be the asymptote. It's gonna get really, really close there. And now we also know there's no way that this could kind of come up like that. That wouldn't make any sense, because the horizontal line is an asymptote, so it has to stay below that. So it's gonna go down just like you see it right there. All right. Well, we have the part in region A. Okay, let's just get 2 points on the other side of 4. And why not just pick 5 and pick 6? Okay, so actually we plugged in 3, we got 0 here. We didn't really need to do 3.5, but I'll just show you real quick. When you do that, 3.5 minus 4 is negative 0.5. That's going to be negative 4 plus 2, which is negative 2. So that's pretty much already on our graph. We didn't have to do that. All right, if we plug in 5, we're going to have 2 over 5 minus 4 plus 2, and that's going to equal 4. And then we have 2 over 6 minus 4 plus 2, and that's going to equal 3. So 5, 4, and 6, 3 are also on our graph. So there's 5, 4, and there is 6, 3. And you can see exactly how it's going to go. If you connect the lines, that's the only way to connect those lines and have them respect those asymptotes. Okay, so it looks like we've shifted to the right 4 and up 2, and it's slightly more stretched out than it would normally be. So that's actually what the picture looks like right there. The domain and the range. The domain is x cannot equal 4 because of this right here, and the range is y cannot equal 2 because we shifted it up 2. So that's the new asymptote right there. Okay, so that is how you graph it. Let me just show you one more picture here. We won't graph it, but it will be done the same way. The vertical asymptote there is negative 1, because that's what would make that 0. So x equals negative 1, and you can see on the picture right here, where is the origin? Yes, here, this green line is x equals negative 1. This right here moves it down 4. So the horizontal asymptote is y equals negative 4, which is right here. The origin is right at that point, just a little bit hard to see there. And you can tell that it's been shifted, it's been kind of reflected upside down. So if you look at the normal parent function, it looks like this. That's how the normal parent function. Notice that this has been kind of shifted around versus that, and that's been kind of shifted. That's because of this negative right here. The negative flipped it over the x-axis. But if you want to get that picture, do it the same way we just did it. You find the asymptotes, find any x and y intercepts, and then just plug in points. That's really the easiest way to do it. All right, last example is a word problem, and these are when they're most commonly used. There's obviously a lot of real-life examples that use rational functions. One of the best examples would be physics problems involving the distance formula. Okay, and that you've probably seen this before if you've taken physics or any kind of science. Distance equals rate times time. Okay, so here's what this says. It says an airline has a non-stop flight between LA and Sydney. A one-way trip is 7,500 miles. So that means distance in this case is 7,500. It says write an equation to represent the travel time. So because we're finding time, we want to take this equation and we want to solve it for t, because we're going to need to know an equation for time specifically. So we solve this by t. T is being multiplied by r. If we were to divide by r, we would get time is equal to distance divided by rate. And that makes sense. If you're driving 120 miles at, let's say, 60 miles an hour. Okay, let me just write that as example. 120 miles, that's supposed to say miles right there. 120 miles at 60 miles an hour, that would give you your time. This is a distance, and that's a rate. And when you divide that, you get 2 hours for time. That's just to show you why that equation hopefully makes sense. So write an equation representing the travel time. Well, distance they tell us is 7,500, so we'll just plug in 7,500 right there. And here's our equation right there. Okay, then it says graph the equation. Any limitations to the range or domain. So the first thing is r has to be greater than 0. You can't have a rate that's negative, and you also can't have a time that's negative. So the time also has to be greater than 0. When you graph this on a graphing calculator, you get this picture right here, but the left part of the graph doesn't actually make sense because you can't have negative rates or negative times. Even if the plane were somehow flying backwards, that would still not be a negative rate. So you can put that in a TI-83 or TI-84 or use Desmos, and that's what the picture looks like. But the only part of this graph that makes sense is this right here. And what it basically says is the faster you fly, this where I just wrote that green arrow, that's faster speeds, and the faster you fly, obviously the less time it takes to get from LA to Sydney. So that's what that graph shows you.